Okay, picture this. I'm holding a standard, everyday coin in my hand. If I just set it down flat on a table, it's pretty obvious, right? It's going to be either heads or tails. There is absolutely no ambiguity. But what if I flick that coin high into the air and it starts spinning really, really fast right in front of you?
While it's just a complete blur of motion in midair, is it heads or is it tails? Think about it. The answer is, well, it's neither. And fundamentally, it's kind of both, all at the exact same time. It's really only when you physically clap your hands together and stop that coin from spinning, when you actually observe it, that it's forced to finally pick a side and become a definitive heads or tails.
Part 1. The Era of the Coin.
So, let's dive into this. That spinning coin, it's not just some fun little thought experiment. It actually perfectly captures the mind-bending foundation of a technology that is, frankly, going to completely rewrite human history. In this explainer, we're going to break down the incredibly complex and, honestly, wildly misunderstood world of quantum computing. We're stripping away all the sci-fi nonsense to see exactly how these machines work, what they look like in the real world, and why massive global industries are basically in an all-out race to harness them. And the absolute core of the whole thing is the qubit. You see, our everyday computers are essentially just giant rooms filled with microscopic light switches called classical bits, and those switches are strictly stuck in either the on or off position, a 1 or a 0. That's it. But a quantum computer uses quantum bits, or qubits, and much like our spinning coin, they exist in what's called a superposition of states. They are kind of both 1 and 0 at the same time, right up until the exact moment they're measured. When you finally measure them, they randomly collapse into a 1 or a 0. But here is the magic part. We can actually control the underlying probabilities of that outcome before the collapse even happens.
Part 2. Classical versus quantum.
Because, understanding what a qubit is one thing, but how does it actually compare to the laptop or phone you're using right now? The biggest thing to grasp here is that quantum computers are not, I repeat, are not just super fast versions of regular computers. They are an entirely different beast altogether. Classical computers, they're the ultimate generalists. From rendering a 4K video to playing a massive video game to just browsing the web, they do all of that everyday stuff incredibly well. Quantum computers, on the flip side, are purpose-built devices. They are completely unsuited for running your word processor. In fact, for most everyday algorithms, they'd actually be slower than those giant clunky computers we first built back in the 1960s. But for a very specific, narrow set of intensely complex math problems, they have the potential to be literally unrivaled.
There's this absolutely brilliant analogy from our source material that perfectly illustrates this dynamic. I love this. Think of your conventional computer as a cheetah. It runs blazingly fast along a set path. But if a massive, sheer cliff suddenly appears right in front of it, it's completely blocked. The cheetah has to turn around and run all the way around the entire mountain just to find the answer. A quantum computer, however, is more like a slow-moving bird. It travels at a fraction of the cheetah's speed. Honestly, a toddler could probably outrun it on flat ground. But when it reaches that exact same cliff, it just effortlessly flies up and right over it. It's accessing completely different dimensions of problem solving.
Part 3. Busting the myths.
All right, before we go any further, we desperately need to clear the air here. The pop science explanations of how these birds actually fly over the mountain have created a massive misunderstanding in the public eye. If you take literally nothing else away from this explainer, please let it be this. The famous myth that quantum computers work by magically testing every single combination, or every password, at the exact same time in parallel universes, yeah, that is almost 100% completely false. It's a super popular idea, but it fundamentally misunderstands the real science. If you just tried all the solutions in a quantum space and took a measurement, you'd basically just get a totally random answer pulled from a probability distribution. You'd actually have to measure it an exponential number of times just to make sure you got the right one. And that would end up being way slower than just doing it on a normal computer. So, let's pop the hood and look at how it actually works. You don't just blindly test everything all at once. Instead, you use this intensely clever algorithm that relies on a property called interference. You start off by setting the initial probability of all your qubits. Then, through incredibly smart operations, you essentially reach in and turn the dials, slowly increasing the probability of the correct answer happening while decreasing the probability of all the wrong answers. You repeat this whole magnification process until the absolute most likely output of the entire machine is the correct solution. Then, and only then, do you finally clap your hands, stop the spinning coins, and measure the system to get your answer. It's not some brute force attack. It's honestly a beautifully choreographed manipulation of probability.
Part 4.
inside the machine.
Okay, so the math is practically magic. But what do these crazy theoretical engines actually look like when you build them in real life? We'll take a look at this stunning structure. It literally looks like a prop from a sci-fi movie, right? In the industry, this is often called a golden chandelier. It's a superconducting quantum computer, and this is the specific architecture heavily favored by massive tech giants like IBM and Google. Now, to make sure those incredibly delicate quantum states, remember our spinning coins? To make sure they don't crash and collapse prematurely, the very bottom of this chandelier houses the quantum chip. And get this, that chip has to be cooled to just a fraction of a degree above absolute zero. That means right there, inside that machine is literally one of the coldest places in the entire known universe. Absolutely wild.
But hey, that is not the only way to build one of these things. Contrast that golden chandelier with this incredible setup. This is a Chinese 76-qubit photon-based quantum computer. So instead of using superconducting circuits in extreme deep freezes, this completely different architecture uses a mesmerizing, labyrinth-like array of mirrors, lenses, and bright red lasers spread across a massive optical table. It literally manipulates individual particles of light. It just goes to show that the hardware race to tame quantum mechanics is still totally wide open, with these wildly different approaches all competing for dominance.
Part 5. Revolutionizing finance.
Which brings us to the most crucial question. Why? Why are the brightest minds on Earth and these massive global corporations pouring billions and billions of dollars into freezing chips and bouncing lasers? What's the actual practical application here? Well, let's look at the financial sector to find out. According to the market analyses we reviewed for this explainer, quantum computing in just the finance and banking sector alone is projected to hit $159.2 million in revenue by the year 2027. We are moving completely out of the theoretical physics lab now and heading straight into the realm of rapid commercial growth and massive investment.
Because when you really think about it, finance is essentially just one giant math problem. It's all about predicting outcomes in highly volatile, multivariable environments, and that is exactly where our quantum bird effortlessly flies right over the cliff. With a quantum computer's unique ability to model millions of complex scenarios through probabilities, big banks are exploring this tech for things like high-frequency trading, deep complex portfolio analysis, precision asset valuation, and advanced risk management. Problems that would literally take our current classical supercomputers thousands of years to optimize. A mature quantum system could theoretically untangle them in just a few hours.
But before we panic about quantum computers instantly taking over the stock market tomorrow or breaking all of our global passwords overnight, we really need a sobering reality check. Way back in the year 2001, researchers successfully used a quantum computer to find the prime factors of the number 15. Great, right? Well, it is now over 2 decades later, and doing that exact same task for the number 21 is still massively out of reach. Why? Because the circuit required to factor the number 21 is over 100 times more expensive and complex to maintain without errors than the one they used for 15. The underlying tech is still very much in its infancy. Scaling up the number of qubits without them crashing out of their incredibly delicate superpositions, that is the grand engineering challenge of our time.
And that leaves us with this final thought to ponder. As organizations steadily chip away at these scaling hurdles and the era of the quantum bird truly takes flight, where does that leave our beloved classical computers? Will the traditional laptops and silicon chips that we rely on every single day eventually become completely obsolete artifacts of a bygone era? Or are we heading toward a future where the cheetahs and the birds work perfectly side by side to solve the greatest mysteries of the universe? It is a fascinating paradigm shift and one you are now well equipped to watch unfold.